I am a GMO, and I believe that you will be too, and so will the people watching this, and they'll say, "Oh no, no, this one." No, it will. If you've already benefited from antibiotics and immunizations and all of the advances we've made in germ theory, we are here, we are living longer and better than ever because of science. And if you can take an injection that will keep you from needing that open heart surgery and all of these barbaric things we do and the terrible ways that we die today, I want you to avoid those. If you could do that with an injection and live a healthier life with your family and your friends, well, I'm going to make that happen. Hi, this is the Buying Time podcast, and my name is Liz Parrish, and this is my co-host.
Hey, my name is Saravanan, and so we have something special for you, something very interesting. Liz, over to you. What special do we have today?
Well, today we're going to talk about what I do for a living outside of having fun with podcasts with Sar. But, it's what I do to actually make the world a better place. And that's what we're going to talk about today.
I know that you are heading a company, BioViva. How long you have been in this? You've been doing this, Liz?
For BioViva, we have been working on our platform for about 8 years.
Okay, and what does this platform intend to do? You finished building the platform, or are you in the process of building the platform?
Well, the idea of the company is to cure biological aging through gene therapy. So gene therapy is a type of technology that you would only take about once every 5 to 10 years, and the genes that we use would upregulate regeneration in your cells, and they would make you feel and look younger. Now, the reason that we're still building the platform is that we know certain genes that are needed to treat biological aging, but we don't know all of the genes. So we're not done yet. But we do have gene candidates all ready to start, and we're already able to start treating specific diseases with these genes.
Can you go into some of the diseases that you treat that are treatable today, and what is there in the roadmap for the next few years' time?
Right. So today, the things that we look at to treat with gene therapy, and we can't say that we have a cure with gene therapy yet in these areas, but in the aging space, we would look at things like dementia, cardiovascular disease, cancer, kidney failure, and COPD. So we look at the biggest killers. But in the gene therapy space as a whole, if you look at all of the gene therapy space, there are already 9 approved gene therapies in the Western world for rare or monogenic diseases that are considered a curative therapy. So right now there is a treatment that has already started in clinical trials for sickle cell anemia that seems to be curing the disease. But as far as the curative gene therapies that are already passed through regulation, there are gene therapies for severe combined immune deficiency, which is boy on the bubble disease. That was considered a deadly disease in the past, but now children can go on to live a healthy life. Lipoprotein lipase deficiency is now cured, one form of congenital blindness, and spinal muscular atrophy, which is also a disease of infants in which they die in the first 6 months to 2 years. It has now a curable treatment with gene therapy. So the space in general is moving quite quickly to curative medicine. Approvals are happening. The difference is my company is looking at the biggest medical unmet need, diseases that kill everyone.
And what is the progress in this field, and what does the roadmap look like, Liz? Because gene therapy is something that people have been talking about for a long time. So how does this, when can I go to a shop and buy gene therapy for myself?
Well, today, if you had one of those rare diseases, you could go get a gene therapy. But for aging, it's a little bit more complex because the regulatory bodies have been slower to approve gene therapies for diseases that are more common. And now we're starting to see big movement in all the regulatory bodies towards wanting to push towards approvals for these type of drugs. So they're at the very beginning. If you were really determined, you could go through medical tourism. The gene therapies are available out in what we call the wild. If you were to do something like that, you would have a company like ours follow your data to ensure that you go through the safest procedure possible and that your data is used towards the betterment of humankind. We can use the data towards clinical trials in the United States.
And so when you say out in the wild, this is what typically Central American countries?
There are countries all over the world. So many countries you can actually do legally a gene therapy with informed consent and an investigator-led study, meaning that a doctor comes forward and says that they want to study a specific therapeutic on a specific patient, and you can meet what's called the Helsinki Protocol, all of the legal boxes of treatment in various countries around the world.
Okay, and what all such things, other than these rare diseases, 9 rare diseases that are legal in the US, the general diseases that you were talking about, what somebody can shop reliably in different parts of the world?
Right. So now today there are a couple of different companies, well, several different medical tourism companies offering a gene called follistatin, which is a gene that we work with. And what follistatin does is it increases your muscle mass. It lowers your glycemic index, and it's considered vastly an enhancement, but actually animal studies show animals living healthier longer. My company did a study that you can find the research paper in PNAS journal, and we were able to extend the lifespan of mice by 31% just with that
Wow.
one gene. They were just flat out healthier, longer, and looked younger longer. And another gene that you can find out in medical tourism is telomerase reverse transcriptase, short telomeres, so the caps of the ends of your chromosomes. Well, let's start from the very basics. Your cells all have chromosomes in them, and your chromosomes house your genes, and your genes are your unique blueprint of why you are the way you are, why you look the way you look, and why your eyes are the color that they are. And but genes express differently in different cells, and that's why there's differentiation. That's why you have eyeballs and you have skin and you have a liver, is because the cells all had the same genes, but they code differently, okay? But your genes are your unique blueprint. But when cells divide, the caps at the ends of the chromosomes that house your genes, get shorter and shorter. And this genetic shortening of these telomeres, these caps cutting off with every cellular division, ends up accelerating aging. And actually there's a multitude of species. There's 24 species, including humans, that our lifespans are tied to how fast the caps of our chromosomes shorten, how fast our telomeres shorten. And so one of the gene therapies is called telomerase reverse transcriptase, and it reverse transcribes the ends of the chromosomes. So in a study that we did with Rutgers University, we showed that if you lengthen the caps of the ends of the chromosomes in mice, it extended their lifespan by 41%. So if I put this in perspective for you, if you were a person who was only going to live, let's say, 80, with telomerase reverse transcriptase, you might easily live to be over 110 if the mouse studies translate to humans exactly. And so this is very exciting, and this has been an area of research for over a decade on both of those genes. Follistatin has been in clinical trials for children with muscular dystrophy, And telomerase reverse transcriptase hopefully soon will get into clinical trials for children with progeria. Progeria is an accelerated aging disease. With them, it's a gene called lamin A. Lamin A is dysfunctional, and their cells therefore create more what's called progerin, and the consequence of that is the quickening of the shortening of the telomeres. And so those children die usually in their teen years of aging associated diseases. They look very old. They can generally now with medicine get to their early 20s. We would like to see them live a regular, if not more than a regular lifespan.
Is it a good way to say that the normal, what we consider to be normal aging, is just an extended progeria because the mechanism is almost similar in both the conditions?
Well, if you ask me, I would say that aging is a disease and that progeria is a faster aging as a consequence. It's just a faster progression of the disease.
So you talked about two different things that are available. Are there any other gene therapies available today? Yes.
Yeah, there's a gene so there's 5 genes that we work with, and 4 of them can be found. One of them is called Clotho. Clotho is named after one of the goddesses who spun the web, the golden thread of life. And it is a gene that's associated with better cognitive performance. So we look at it as being one of the gene candidates for dementia. It's also associated with protecting the body against cardiovascular disease and chronic kidney disease, which affect all of the population. If you live long enough, your kidneys will fail and you will certainly have some sort of cardiovascular outcome. So that's a very exciting gene. And then the last one that I know of that's in medical tourism that's based around aging is called PGC1 alpha. And so your cells have mitochondria in them, and your mitochondria are like the powerhouse of the cell. They're all of the energy that helps you clear up damage and, sort out debris and make sure that things are coding correctly. Well, PGC1 alpha makes it so your cells have more and more robust mitochondria. So they're like an energy source. And that sort of gene, all of these genes are associated with extending lifespan in model organisms with no negative side effects, by the way. This gene is upregulated when you exercise. So when people exercise a lot and they look better, you meet somebody and you haven't seen them for a while and they're like, well, for 6 weeks I've been exercising, I've been on this diet and exercise thing, and it's PGC1 alpha is like the powerhouse of why they look so good. But when you artificially upregulate it, it's probably good for things like metabolic disorder, things like type 2 diabetes and obesity. So also it's anything that increases your mitochondria, helps your brain function, everything else. So Alzheimer's and Parkinson's disease have also been candidate diseases to treat with that gene.
And how do people who have something like fibromyalgia, which is very often a mitochondrial dysfunction disease, do they benefit from this treatment?
Well, that is something that needs to be studied. And, that's where a company like ours steps in and we look for funding, and then we go after specific diseases to help a specific cohort of people with disease.
These gene therapies, how is it actually done? How does it look like? Somebody wants to get a gene therapy. Let's say I want to get a gene therapy and I want, I don't know, maybe my telomeres, maybe my muscles are made bigger, and maybe my mitochondria are upregulated so I can go and work in the gym and make the muscles even bigger. So
That's right.
how does it look?
So people think, oh my gosh, gene therapy, what is this? What is this, technology? And how would that present? Because we're really living in a sick care system. We live in a reactionary system in which not until your parents, get chest pain do they open up their chest and open heart surgery. They might have to put in a pig's heart valve, like a million things go wrong and we take care of them. With gene therapy, it literally is just an injection, usually an IV, but with muscle enhancing gene therapy, with follistatin, it's generally a series of intramuscular injections and probably takes at most 20 minutes, and then you're off to the rest of your life. And then you might look at retreatment in 5 to 10 years.
So I remember having seen in one of the Jason Bourne movies that, after one of this gene modification, the hero gets a fever for something because it's got a viral vector that administers the mutation. Is it something like this? And you just get the injection and then you walk off, or you need to be around in the place for a few days and then leave?
You generally are in the location for a few days. In some cases, people will get a mild fever with gene therapy, and that's unfortunately not a very good sign. It means that your immune system has been alerted to the gene therapy, and it means that you'll probably get lower output out of your gene therapy. So with a gene therapy, we generally try to do immunosuppression, meaning that we suppress your immune system, not to the point that you would get sick from the air around you or something, but we would suppress your immune system. So we're trying to turn down the immune system so that your body doesn't recognize the therapeutic. When vectors are used to deliver gene therapy, they cannot multiply. You cannot give somebody something that can actually produce more of itself. That's against the law, really. So we can only give you what's called attenuated vectors, meaning that they can't multiply, and so we have to put in as many as we can for a therapeutic effect. Again, if you get a fever, that's pretty much today the worst outcome from gene therapy. You literally probably would have less of a positive response from the gene therapy.
That's very nice. You could.
We try to avoid that.
Okay, got it. And this is like the single injection, or you are saying multiple injection? If it is multiple injection, what it's spaced? How many days it's done?
So you would have it all done in one day, and if the protocol was intramuscular injection because you're trying to focus on certain areas of your body, you would get injections into those areas. The great thing about the follistatin gene, the one that increases muscle mass, is that it's a shared protein. So you could put it in your arms, but all of your body will have benefits to the skeletal muscular system. So you could take it by IV. A lot of it would be absorbed by your liver. So some doctors like to give it intramuscularly directly where the patient wants the best effect. When we think about that, we think about, building our muscles, because that's very cool. I did that gene therapy and I enjoyed the muscle gain personally. But the glycemic control of follistatin is really where its superpower comes from. So increasing muscle mass increases insulin sensitivity. And that is a game changer for diseases like type 2 diabetes and metabolic syndrome that build on us as we age, fatty liver disease. There's a recent overview of follistatin. There's so many research projects on follistatin that the analysis of a multitude of reviews was amazing. And actually, it's believed that it may even protect people from several forms of cancer. It's an amazing thing, but it's because of what the gene does. So the gene doesn't just help you gain muscle mass. It blocks something called myostatin. And myostatin is a muscle inhibitor. It's kind of an evolutionary thing that happened to us so that we wouldn't, be in a grow and go mode all of the time. The problem is that myostatin leads to sarcopenia. So people over the age of 35 start to lose muscle mass by about 1% a year from that point on. Now, that's not 1% to 100% over, a certain amount of time. That's 1% of the 100% that you have at that time. And that muscle wasting is actually very serious. It leads to frailty, falls, broken hips, accidents, and ultimately to a lot of people's death because they are unable to heal and they give up later in life. So increasing your muscle mass is actually directly in like it's a direct outcome to longer lived lives. So when we look at all cause mortality, people with more muscle mass live longer, is what I mean to say. And but they also have better glycemic control. So, for me, I think that the superpower of the gene is the glycemic control over even the muscle mass, but it's a byproduct of that muscle mass gain.
Look, I have another question. So when you say muscle mass gain, is it that every muscle fiber that you have, it becomes bigger, or people produce new muscle fibers? Is it a hypertrophy or is it hyperplasia?
That is actually a really good question, because we do think that younger people gain more muscle mass by muscle fiber. But the big test is to test people over the age of 65, when the dwindling stem cells that are associated with muscle are an issue. And if we can actually just create more robust and denser tissue, or if we can actually help an aging population gain more muscle fibers.
How was your experience with this gene therapy? You said you went through it and you saw the benefit. Take us through it. So that'll be an inspiration.
Right. So my story started with my son. I had been volunteering for 2 years for the advocacy of the use of stem cells, and I had learned a lot about stem cells, and I had fallen in love with the genetics behind stem cells. And that's kind of why we started talking about cells and cell differentiation, different cell types, what makes us, able to do, a multi-super organism, right? But stem cells are particularly fascinating because they can heal tissues. They have a regenerative effect. And the genes behind them were quite fascinating to me. So in that way, I fell in love with genetics. But 2 years into the project of working with the stem cell groups, my son was diagnosed with type 1 diabetes, and he was 9 years old. And I ended up in the world of sick children. You go to Children's Hospital and you have to stay there until you can control and help manage your child's chronic condition. And there are kids there who are dying of diseases, and even type 1 diabetes itself is a very dangerous disease on a daily basis. It's not an easy disease. It's not like type 2, where at a certain point of your life you can do diet and exercise and get it under control. Type 1 is an autoimmune condition, meaning that your own body attacked your pancreas and is destroying the islet and beta cells and their ability to create insulin. Insulin is a hormone that allows our cells to uptake sugar and use it for energy. So my son was eating food, but he was dying. He was dying because his cells couldn't use the sugar, the energy in the food at all. And he was wasting away, and we found out it was type 1, and we ended up there. And I really, at that point, committed my entire life to solving these childhood diseases. And that I ran into the aging research was just merely by chance, because I was looking for conferences that were talking about genetics, and I had an opportunity to go to a conference in the UK that had the professor of genetics from Harvard, George Church, speaking at it. And to this day, he is a founder of my company, by the way. So that ended up working out really well. But anyway, I learned about all of these these gene therapies around treating biological aging. And my company, every gene that we work with will treat an aging, part of aging, a hallmark of aging. We can talk about the hallmarks of aging if you want, but they'll also treat a childhood disease. And that's the mission of the company, is to bring these drugs to the world so that these children can be cured of their diseases, but then not just die of the same old diseases that we all die from, that they could go on and live a healthy lifespan and get back some years and enjoy them. So, so in 2013, I learned about a bunch of aging-associated gene therapies. In 2015, BioViva, my company, was started, and the first money that came into the company, we built 2 gene therapies, telomerase reverse transcriptase, which had never been used in a human, and follistatin, because we felt that the 2 gene therapies would be synergistic and treat different parts of aging. And I flew out of the country and I took those gene therapies. And so I was in my mid-40s at the time, and I'm 52 now. And I would hands down say that I feel healthier now than I did before I took those gene therapies. And I've taken gene therapies since, and I will continue to do that. I'm sold that this is the future, and this is a more radical way in which we can get back major losses that we lose over time, even with the best diet and exercise. The gene therapies will be the game changer.
I think we should probably start this podcast saying, how old are you and how old am I? And that itself could be an inspiration for a lot of people. So this is what, in 2015, you took this gene therapy first, is it? Yes?
Yeah.
And what was the measurable changes? So let's say somebody gets it today, and probably today it's a lot more elegant than what it used to be back then. Maybe the process might have been more streamlined and things like that. So what did you did this out of, I don't know, a sense of mission? What did you feel after a week after that, after a month after that? And was there any response from people around you, from your husband, from your family, from your friends?
Well, I mean, so it was the first test in gene therapy with telomerase reverse transcriptase. And back then, they knew that it could lengthen the lifespan of model organisms. Any test that they did with it, it was beneficial. What they didn't know is whether or not it would cause cancer. And even though we have shown over and over again in model organisms that actually reduces the risk of cancer to lengthen your telomeres, it still was questionable. So the first gene therapy, the one that I took, was very different than what someone would take today. Like I told you, today you would take an IV, you might sit in a chair, you might take 20 minutes, and then you're probably going to go out to eat at a restaurant in your hotel. At that point, so when I did it, we had to test a multitude of areas because I didn't want anyone doing the gene therapy who might get sick. So we had to test areas all over my body, high risk areas, my breasts, areas that had been exposed to a lot of sun. Anywhere that was a high cancer risk area, I was injected into those areas. And so I probably was injected over 100 times, and it was not very it was not very exciting. It was really a sense of duty. There was a slow change in myself and in my body. I think over the next 3 to 6 months, I definitely felt muscle mass gain from the follistatin. But the telomerase, I think, people now say, oh my gosh, you look so much younger than you did then. And that's so nice. I think that it really took years to make visible changes, but immediately we could test the telomeres and see that they were longer. And so that part was really neat. Since then, when I've taken gene therapy, of course, now I just get to do the IV.
Fantastic. You also took other gene therapies subsequently. What were the other ones? It's the same thing you repeated, or is it something else that you did?
I did Clotho, the gene that I was talking to you about that's for chronic kidney disease, dementia, and cardiovascular disease, and I took PGC1 alpha.
Okay, now Kyoto, if it's meant for, okay, your kidneys are good, your cardiovascular system, I presume it's good, and you are mentally very sharp. So did it really make a perceptible difference? I know that you did it just so you know what is happening, and typically that's what I do as well. But did you see any perceptible difference from?
Well, I mean, I really felt that it helped me a lot with my company. Now, I scored higher on an IQ test after I did Clotho, but I don't know. Maybe that's because I was more prepared the second time.
How many points higher?
15.
Wow, one full standard deviation. Wow, that's big. That's really huge. Uh, this is probably the very first time I'm hearing about something that can reliably increase the IQ.
Well, now we have to do the gene therapy in 100 and then 1,000 and then 10,000 and then, more people to see if we can reliably get that uh, benefit. Now, we did facilitate the data analysis of a offshore clinical trial, an investigator-led study of 5 patients with dementia, and 4 out of 5 of them had cognitive benefits. I mean, cognitive benefits that were the exact opposite of what you see in Alzheimer's. Generally, in dementia, you see a natural progression of, well, lowering scores. And the best that anyone has ever been able to do is slow the lowering of the score, but our gene therapy actually increased the cognitive response of 4 out of 5 of the patients. And that was amazing. So, that's what did I do this week? This week, we're getting all of our literature together to go to our pre-IND meeting for seeing if the regulatory system will allow that therapy to go into humans in the US.
That's lovely. By any chance, does this work with other neurodegenerative diseases like Parkinson's and MND motor neuron diseases, ALS, and all that? Or they are on a different axis?
They're slightly different, but we're hoping so. So Parkinson's might also be a great candidate for the same combinatorial gene therapy that we're using for dementia. Frontal temporal dementia may respond to it as well as Alzheimer's, just because the mechanism of the genes, because they're treating aging. They're not just trying to treat a symptom like beta amyloid plaques. Clotho is the one that we're looking at that may have some benefits to ALS, but we don't know. It does seem to help with the protection of the myelin sheath, but we don't know if it can repair it once it's damaged. So this is all new territory, and yes, it should be moving much faster. I took those gene therapies in 2015. I mean, there should be no regulatory body right now that is blocking those therapies from access to those type of patients.
That's true. And your PGC1 alpha also was taken in 2015, or was it later than that?
That was 2020. Clotho and PGC1 alpha were 2020.
Usually, skin, nail, and other things very often is thought of as cosmetic, but they are true indicators of inner health. And after you had your mitochondrial function enhanced, was there a visible change on yourself?
I think that people have said there has been a visible change on me over the several years since I took the first gene therapies and then again after the next gene therapies. I mean, it's really tough because we haven't cured all of aging. So let's talk a little bit about the hallmarks of aging. So there were originally 9 hallmarks of aging. And what that means, these hallmarks are the things that are happening at the cellular level that drive the reasons why we kind of decay over time, right? Aging is cellular degeneration over time and probably vastly programmed, right? So we're programmed to get through a meet, mate, birth children phase, and then we kind of start to become less important to evolution at that point. So, however you see it, this degeneration over time is actually driven by hallmarks of aging. And there are things like telomere attrition, mitochondrial dysfunction, cellular senescence. Senescent cells are cells that are old cells. They no longer function as regular cells. They cannot divide anymore. And unfortunately, they tend to send off a lot of inflammatory markers to the rest of the body. But this list of 9 hallmarks are the things that we're targeting with gene therapies. And recently it grew to 12, and now it's estimated to be at 24. Although some of the hallmarks are things that are downstream of the original hallmarks, like inflammation. Inflammation happens because of cellular senescence, mitochondrial dysfunction, telomere shortening, and genomic instability. But we don't have to go there. What you do need to know is there are these hallmarks, and even the original 9 hallmarks, we don't have a gene therapy for all 9 of them. So in order to reverse all of aging, that is what we're running for. We are trying to find the genes that can reverse all of the hallmarks of aging. Now, what will a therapy look like? I think that realistically, in the next 10 to 15 years, a therapy will be a chimeric kind of therapy. It'll be like gene therapy, stem cells, diet and exercise, and about 5 key small molecules. So there'll be small molecules to reduce your stem cell, or not your stem cell load. You want to increase your stem cell load. There'll be small molecules to reduce your senescent cell load. There will be small molecules to reduce your glycation endpoints, all of these things that are building up between cells, and the list will go on. So we'll be able to target some of them with gene therapy, some of them with small molecules, some of them like stem cell depletion with stem cell injections, probably your own cloned stem cells, and then, lifestyle will play a major role in it. Your diet and exercise, if you want everything to be right, you got to feed your body what it needs and treat it as it needs to be treated. So it's complex. Hopefully, though, I'm hoping that in the long run, we will eventually have a gene therapy that you can inject that will target all of aging, so you can just set it and forget it.
That sounds like a science fiction, but I think you're already living a science fiction.
Oh, it is now. I am a GMO, and I am more for GMOs than ever before, and I believe that you will be too, and so will the people watching this, and they'll say, "Oh no, this one." No, it will. If you've already benefited from antibiotics and immunizations and all of the advances we've made in germ theory, we are living longer and better than ever because of science. And if you can take an injection that will keep you from needing that open heart surgery and all of these barbaric things we do and the terrible ways that we die today, I want you to avoid those. If you could do that with an injection and live a healthier life with your family and your friends, well, I'm going to make that happen.
Yeah, I'd like to understand so much more about it. So you were saying that you are running to make this happen faster. So what should happen for you to do this faster so more number of people get to benefit? See, there is one thing that's unusual about healthcare. If Steve Jobs didn't come out with this iPhone in 2008, probably somebody else would have come out with it in 2012 or 15 or whatever. It's just inevitability. It's just a matter of few years. And nothing much would have been lost from all of our lives in case if all these innovations happen a bit later. But in healthcare, innovations come later. There are many people who have, by then, they left the face of the earth. So many of these things that you do now, if someone gets these enhancement or get these things that make people healthier, if they get it faster today, then, imagine somebody who's in 75 and then they get it today, the chances of them turning the things around is so much better than getting it at 80, getting it at 85, even if they continue to be there. Some of them may not be there. there is tremendous amount of human value in getting this done as fast as possible. So, what should happen for this to accelerate?
Well, that's what I work on in all my spare time, which isn't much. I work on the regulatory side of finding ways that we can work with governments to expedite approvals for people who need them. I work on a project called Best Choice Medicine, and we're working on the Best Choice Medicine Act of 2023 right now, which is an accelerated route for gene therapies. So, as you said, of every year that we wait, and let's just preface this with healthcare is the most heavily regulated area in all of human existence. And it was regulated so that people couldn't bring bad drugs and make money off of bad drugs that might harm people. But now the overregulation, the risk aversion, and reactionary healthcare, meaning that only if somebody's really bad off can they get access to something, and even yet then they most likely can't because of risk aversion of medical doctors. 41 million people will die this year of aging-associated non-communicable diseases. Okay, these are people who could be participating in technologies that I took and potentially still be living on the planet. 15 million of that 41 million people who die of aging-associated diseases die prematurely due to bad exercise, bad diet, and various things that are making the aging go faster in their body than it should. So when we're working in a heavily regulated area, the only thing we can do is try to work with the regulators and work with the general public to teach them about new technology. Remember, it doesn't matter who you think you are. You are a powerful person, and people demanding access to medicine is always what has changed medicine. From HIV to a myriad of other diseases, it wasn't until patients demanded access that the government then conceded and gave them access to those medicines. So you can push the technology forward by demanding from your government that they start to treat biological aging conditions as a necessary and medical mandate. So that's one thing. But we can also ask the regulators to make changes. And so the Best Choice Medicine Act of 2023 is essentially an accelerated route for terminally ill patients to get access to gene therapy pre-regulatory in a safe way so that they don't have to travel outside of the country or go somewhere where they might not, know the people or trust the people who are doing technologies. I'm working on a route that would help you get access to that technology locally. And this will be a very hard push, but it's absolutely necessary to save millions of people's lives, because those people dying is like burning books. Those are stories. That is experience. And if we could keep them on the planet, imagine. Countries are actually, the Industrial Revolution happened on the back of how long people live. If we could have people living longer today than they would have before, imagine the innovations that we can make. Imagine how we could save the planet. Imagine how much better we would be treating each other if we knew that we would be here long enough to suffer the consequences if we didn't do those things.
So, from what you're saying, it looks like regulation is the biggest drag on the progress of this.
Absolutely. Absolutely. Of all the gene therapies approved for use, they have not approved anything for a condition that afflicts the entire population as aging does. So let's put things into perspective. So there are several gene therapies for cancer now. And that's fantastic, because boy, do we want a cure for cancer. Cancer is stochastic, meaning that it can come from a myriad of places: your environment, radiation, something that happened maybe that you were exposed to when you were young. So there's a lot of reasons that cancer happens. And so, of course, we want to cure cancer. But if you cured cancer today, listen, if you cured all of cancer today, the average person only lives 2 to 4 years longer. And that's only the average person who would have died of cancer, which isn't everyone's shortest fuse. When you think of aging, think of short fuses. Some people it's cardiovascular disease, some people it's their kidneys, it's nephropathies. For some people it's dementia. If you cure one of them, you don't significantly extend lifespan. You have to go after aging. You have to make the cells behave as they were when they were youthful. They need to clear up the damage. The DNA needs to read correctly. There was just a paper out this week talking about in aging people, there's some sort of genetic mutation. We start coding the wrong proteins. We start coding proteins for genes that are not even supposed to be turned on in a youthful state. So if we go after aging, we could actually take all of these diseases and at least slow their progression.
It was extremely hard hitting to hear you say that if you cured all of cancer, all that we would do is extend the lifespan by about 2 to 4 years' time. That's an argument that nobody can refute.
Because all of the diseases of aging are actually progressing in your body right now. So that's why people don't understand that we want you to get chronologically older. Getting older isn't a disease. Biologically getting old is a disease. And we get biologically old at different rates. And that's why you could have, if I had 10 people here with me and they were all my age, somebody might die this year, somebody might die in their 60s, somebody in their 80s, and a couple of the people might live to be well over 100, okay? But the reason is because that we're aging at different rates and we're dying of everything. It's just the shortest fuse is what we're diagnosed with. And how many people do you know who are over the age of 65 or 70 and they're on blood pressure medicine, they're on something to protect their liver, some sort of Legasil or something. They're having their kidneys examined regularly because they're basically having kidney failure over time. They're slowly losing their memory. It's just not what it used to be. That's dementia coming. It's all running. You're dying of heart disease. You're dying of kidney failure. You're dying of liver failure. You're dying of dementia, and you're slowly burning the fuse to cancer. It sounds really depressing, and this is what I do with my entire life now, is focused on this. It's so important, and that's why I work all the time, but I don't consider it work because it really is my passion. But it is hard, it is grueling, and it is ugly, but it's the only way we're going to get to the other side. We have to face it. We have to understand it. You have to understand it as an advocate. You need to understand that you are the patient. You will be the patient eventually. And you need to understand it as a motivator to doing something about it. And you can take the lead on any one of those things, but I take the lead on all three of them. I am here to change things, but I am inevitably the patient if I don't. There is nothing more pressing than this for everyone watching this.
You're so passionate about it, Liz. Probably 10 people like you will change the future of humanity. I'm so proud to be doing this podcast along with you than with anybody else. The passion that I'm seeing is phenomenal. I'm so proud of being your co-host.
Well, I'm proud to be here with you too, because the next podcast is going to be about what you do, and you are just as committed as I am, and that's how we met.
I'm going to have two more questions that come to my mind about gene therapy. Can we finish it? Can we go at it? I hope you're doing good on time, I think. So first question is, now a lot of big companies are getting into gene therapy. So is it likely to change the regulatory environment, or because CRISPR and other people are essentially focusing only on disease reversal, that is not going to have a big impact on your regulatory environment in the US?
It's having a big impact. So large companies who once made small molecules and made some of the drugs that you're taking today are starting to get very interested in gene therapy. Many of them have already acquired companies and that, of course, as you know, is the biggest move towards changing regulatory, is changing the lobbyists of regulatory. So I think that that's why we're starting to see the shift in the regulatory space. Plus, there is also more demand than ever, and there are people out there like me who are saying, we need to get moving. You know, we're showing that in human bodies, this is safe, this is effective. And the one thing that the world isn't ready for, shockingly, because everybody's always asking me, what are the side effects of gene therapy? We're so used to taking bad drugs that, for instance, statins, keep taking them, whatever, if your doctors prescribe them. They're trying to lower your LDL cholesterol, and they're trying to keep you from having a stroke. But if you look at the Cochrane report and you look at the number to harm and the number to help, in the long run, they will help some people. And if you're one of those people, you should keep taking them. But for many other people, they drive type 2 diabetes. 1 in 4 people will get type 2 diabetes, and 1 in 10 will get dementia from taking those pills. So I'm not saying don't take them, but we're just so used to side effects. And then we end up taking more drugs because of the side effect of another drug. It was estimated that, people over the age of 65 in the United States are taking about 6 drugs, prescription pills, and some of them are just to manage the side effects of other pills. With gene therapy, we're actually harnessing what nature already does, and we're just putting healthy genes into your cells that upregulate for human proteins that are associated with better cellular outcome. So it's just so mind-boggling, I know, to say, oh, you took a bunch of gene therapies, but what are the side effects? What bad things are happening? And there are not bad things happening from these specific genes. It could happen from the wrong genes. That's why there's a lot of research that goes in before humans use these drugs.
Approximately, what is the kind of budget that somebody should keep in mind today for them to get one of these gene therapies?
Oh, that's a really hard one. Okay. So gene therapy today is considered the most expensive drug on the planet. So of all the regulated gene therapies in the United States, the cheapest gene therapy is $425,000 US for one eye. If your child is born with spinal muscular atrophy, meaning they would die within 6 weeks to 2 years, the gene therapy is between $2 and $5 million. I think that's inherently wrong. By treating the biggest medical unmet need, aging, we can actually create affordable therapies. But right now they're cost prohibitive. So if you were going to go to something like medical tourism, it's not going to be like paying for a regulated gene therapy. It's not going to cost you millions of dollars, but it really is super expensive. It's going to be probably over $100,000, which is way too much for most people. So democratizing gene therapy and getting it into more people's hands is what will lower the cost. So that's why we're pushing for regulatory approval for these therapies. I mean, companies could just go medical tourism and, make money from rich people who can afford the technology, but I would like therapies for everyone to be affordable. It's more fun with everyone, driving us all crazy. People are always like, wait a minute, you want everyone to live longer? And I'm like, yeah, it's the craziness that makes life so cool.
I've learned so much about gene therapy today, Liz. It's not an area that we have been focusing on, and at Amura, we largely work on nutrition and hormones and things like that. And to know so much and to understand the possibilities that exist today, and to know that this cost could come down and the mass adoption is on the way. These are all really exciting. You also wanted to share a lot of things about what has happened in your industry in the last 1 week. Do you have that?
Yes, I do. So I already shared with you one of the things that happened this week in my space, and that was a study of aging genomes and how genes code as we age. Not very well. Lots of junk out there and RNA sequences that are probably contributing to aging. Oh, there was an interesting article in the Economic Times that was basically the title is Children Born Now Could Live to 100 Years. Companies Must Change Their View of Age. Isn't that cool? So basically, what that's saying is that economically, if you have a company, you have to be prepared for people living longer than ever. So when I started this in 2015, I believe it was estimated that people living over the age of 100 was growing by 1,024%. So that doesn't mean like a multitude more people. It means 1,024% more people than historically have will live to be over the age of 100. And now, even in the Economic Times, they're talking about it. Aging across multiple organ systems. So basically, there's a lot of diversity that's happening that's causing a lot of problems between organs and cells. Let's see. Cold temperature extends longevity and prevents disease. So, I think that in your area, especially, you've been hearing a lot of people talk about, cold pressures and cold showers, running out and jumping into cold lakes as a form of longevity benefit. And one of the reasons that probably works is something similar to PGC1 alpha that we talked about earlier. White fat turning to brown fat is fat that's full of mitochondria, right? So your mitochondria really kick up and say, oh man, it's cold. Let's see, short telomeres linked to cancer. So this was a great paper that was put out that showed that not long telomeres, short telomeres are one of the major reasons why we get cancer. So when your telomeres get short, those are the caps of the ends of your chromosomes, you basically start to get what's called genomic instability. The chromosome is no longer packed tightly and cared for by the telomeric ends, and that leads to genomic instability that leads to cancer. Also found this week in a study was that short telomeres are certainly in the brain associated with Parkinson's, Alzheimer's disease, and a variety of dementias. So short telomeres were found in the brains of people who suffered from those conditions at various ages. So your telomeres can shorten at different ages. Let's see, there were a couple stories about young people who are now like living active and healthy lives after they've taken gene therapy. So gene therapy, again, is not just something for old people. There are miraculous stories where children's families are coming forward and sharing pictures after their children who had life debilitating or high mortality diseases were given gene therapy and are now living robust lives. So I think that was pretty much it for my space this week. And you can tell every week is amazing now. So many papers come out every week about aging, and that's not even what's happening with businesses. You should see the press releases. It's just one after another. So it's a very exciting time for gene therapy.
And people who have taken this path in the past and are a living testament for the benefit it could bring, I think it's the inspiration that rest of humanity needs at this time. So I should say that thank you that you took the risk of being one of the first people to get this done way back in 2015, and then you say that, hey, you know what, I did this long ago, 7-8 years. There is so much of progress that has happened. I have something interesting book came out in the space of longevity called Outlive. The book has a lot of press and it's become the bestseller instantaneously because it is written by a podcaster, very well-known podcaster. He's a doctor. He's called Peter Attia. He's known for his keen understanding of conventional medicine. It covers a lot of things about importance of diet, importance of exercise, and squaring the aging curve and things like that. Most of the things are like a primer for anybody who wants to uh, think about living much longer. Nothing as advanced as what you are talking about today. But if somebody is thinking about getting inspired about living much longer, this would be a right book for them to pick up and start reading. The title of the book is Outlive.
Yeah, I saw that. And actually, so I have not read the book, but I have my Audible tokens right here, by the way, that I'm going to cash in and get the book. I did see the Guardian article about it, and he does talk about gene and cell therapies in that article, and how that he believes that those are the future, the technologies that will help us ultimately break what we call the bottleneck, the longest that humans can live. And so sometimes when we get in conversations, we don't want to, jump forward and say, how long could we live? Because then we become very speculative and wondering and everything else. But if we can live healthy longer, that would be the key. So, yeah, I am excited to read his book.
That's very insightful conversation. I learned so much about gene therapy, and we don't have a lot of it at Amura. We do a lot of other things about health. We don't do much about gene therapy. I've learned so much, and I'm looking forward to getting into it sometime soon, maybe with your help. Thanks a lot. And listeners, I hope that you enjoyed it as much as I did listening to Liz and her adventures and the kind of results that she has for all of us to see. Thanks for sharing it, Liz.
Thanks for having me. And if you come to a podcast and you're all muscled up, everyone will know we won't have to say anything.
How I wish. Yeah. Thanks a lot. Bye. Have a good evening.
Thank you so much. I had a great time, and we'll see you next
Thank
week.
you. Bye bye.